Right, let's have a look at projectiles. So a projectile could be anything that sort of rolls off a cliff with a certain speed, or could be just dropped off a cliff, or you could throw something into the air and it'll follow a parabolic path. And all these sort of motions here, whether it's going parabolic, straight down or straight up and down, they could be termed projectiles. They all have a few things in common. First of all, it turns out that the horizontal and the vertical components are independent of each other. So in other words, no matter how fast the ball is actually sort of shot sideways, it would still fall to the ground at the same rate. So I would expect this ball that's been moving sideways here and landing to hit the ground at the same time as the ball that's been dropped straight down. Because the vertical component here, the fact that it gets faster and how long it takes to get to the ground here, those components there are not actually affected by the horizontal speed or horizontal velocity. What would happen is if you were to fire this faster off to the side, the ball would actually just travel further in the same time, but still land together with these other balls. Okay? So horizontal motion and vertical motion does not affect each other, so they are independent. Other things to bear in mind is that the horizontal velocity of all of those would be constant because there's no force acting in that direction, and therefore there should be no acceleration, and that's ignoring air resistance. So we expect the horizontal velocity to stay the same throughout the whole trip there in stage 1 certainly. Whereas the vertical velocity here will undergo a constant acceleration because the force of gravity is always constant in size and direction going downwards, so you get an acceleration of minus 9.8 the whole time. Now the result of these two parts here is you'll get a parabolic path there, or a curved path for something that's hit or thrown sideways. So if you look at these here, what's going to happen is the black arrow there represents that 8 metres a second, and that horizontal velocity component is going to be the same all the way through if a ball's thrown sideways there or something rolls sideways. And that stays the same all the way through this motion here. Okay? Whereas vertically it might start off with 0 vertical velocity, and then it's picking up velocity here, going to 1 metre per second, and then 3 metres a second, and 6, and so on. And the result of those two combined factors there, a constant horizontal velocity and an increasing vertical, would be this total velocity vector here, where the velocity vector gets longer and also gets to a steeper angle. And you can see that sketch of it there. So that's the combined effect of that sort of thing. So you need to use those when you actually answer questions on this. So a typical question you could get for this would be something like a ball here rolling off a cliff with a velocity of 5 metres per second horizontally. We might make the cliff, say, 8 metres high here. So the ball's going to go that sort of a motion where it travels like that and lands a certain distance away. And they might ask you some typical things like what's the time to impact, how long does it actually take the ball to crash there? And what's the range of the ball, or horizontal distance from the base of the cliff there? And they might ask you for the impact velocity, how fast it's going when it actually strikes the ground there, when it comes down. So there's some typical questions you can get for this. So I like to actually do this in separate columns there, so that you keep the horizontal and vertical motion independent of each other, and you don't use the wrong quantities in the wrong direction. So it's always going to have an acceleration in the horizontal direction, the horizon sideways, of 0 metres per second, because it keeps the same horizontal velocity. Vertically though, it's going to accelerate downwards at minus 9.8 all the time. We're ignoring air resistance. Now this ball here has been fired sideways at 5 metres a second, so that's actually its starting velocity in the horizontal direction. So VO would be 5 metres sideways here, 1 metres per second. And vertically, it does not have any velocity up or down to start with. It's not being fired upwards or downwards, so we're expecting that to have a velocity of 0 to start with. So these are fairly typical quantities to be putting in there. That A is equal to 0 for all your questions you're doing. A is minus 9.8 for the questions. And quite often, if it was a car driven off sideways or a ball thrown sideways, that's going to be fairly much common. Now, the other information in this particular question is that the ball's dropping down 8 metres. So we actually know that it's going to go down 8 metres. So the minus 8 means it's gone down 8 metres. All right. So now we come to the questions here. Time for the ball to land. Question 1. I would do that over here where you've got more information to work with. Okay? So we need an equation there which actually have all those in. And this is the fairly common equation you use all the time. So if you substitute, you get minus 8 equals. Now the VO is worth 0 here. So we should be able to just sort of cross all that out there, because 0 times by anything is 0. And then you're going to get a half of minus 9.8 times by t squared, that's what that means. Now half of minus 9.8 is always going to be minus 4.9, so you'll get into the habit of doing that. And that's timesing by t squared. So to solve for t squared, we need to get rid of this times here. So we would divide by minus 4.9 to get rid of it. It's very common for people to actually do this as, oh, this is subtract 4.9, I'm going to add 4.9 on the other side. But that's not what the operation is. You're doing the opposite of timesing by minus 4.9, you need to divide by it. So to solve that, we're going to square root that to get rid of t squared, and the 8 and the 4.9s are going to top each other, because the negatives will cancel. And you do the square root of 8 over 4.9. So that's 1.63 square rooted, and that gives you a square root answer of about 1.28 seconds. So that's part one then. You can actually use this time up in here now and transfer it over. It is the only quantity out of all of these which is a scalar which can go between the two columns. And that's important because to do this next part, part two is to work out the range. So if you want to work out the range now, you're actually doing the range in the horizontal direction here. We're trying to find out horizontally how far is that object going to travel sideways here. How far is this going horizontally there? So we're going to do this in the horizontal. And fortunately, you can do the same equation again. It's exactly the same stuff here, but the difference is that the acceleration is 0. So the half times by 0 times t squared, that all is going to be 0. So you've got a range here of VO as 5 metres a second sideways for a time period of 1.28 seconds. We could transfer that over. And you get 6.4 metres. So you get 6.4 metres and it's going to go sideways that way. Now the last typical question you'll get here is how fast is it going when it hits the ground? So if you look at that, as it hits the ground there and comes down, it's got a velocity that's coming down this way, and that's got to be based on two velocities, a sideways and a vertical, horizontal and a vertical. So we need to know what these parts here are to work out that total vector. Now fortunately, horizontally, if you check it out here, Vt would equal VO plus At, trying to find the velocity here at a time t seconds later. But in the horizontal direction, A is 0, so that whole thing will disappear. The A is 0 here. So that can disappear. Which means it just stays the same as before, 5 metres a second still going sideways. So that has not changed. But vertically it will change because it's accelerating with gravity. And while the initial velocity is 0 vertically, and that's what I mean about not mixing these up, it's important to get the 0 from here and not put the 5 in, okay? If you do that, it's a minus 9.8 for gravity and a time of 1.28 seconds. That'll tell you your final vertical velocity, which is close enough to minus 12.5 metres a second, or you can think of that as 12.5 going downwards. So, you have now got two velocities here that you need to look at to get a total. We want to add one velocity to the other velocity to work out what that total vector there is with an angle. What is that total there? Add together with a vector diagram, which is why I taught you this. So if you do this as a vector diagram, that will be your total velocity there with an angle. Vt should be the square root of 5 squared plus 12 squared. It's that. It's around about 13.5, I think, metres per second. And the angle here is tan to the minus 1 of opposite side over adjacent side. Okay, and as I said, if you don't like using these, you just do a scale diagram of that and get the answer. So don't forget, this is based on the idea that the vertical motion is not going to be affected by the horizontal motion. You can see this multi-image diagram here, where they might have taken maybe 20 flashes per second. The balls, one's been dropped straight down, the red one, the yellow one's been fired sideways, but the balls are still falling to the ground at the same rate because you can tell that the images are at the same height each time there. So therefore the vertical motion has not been affected by the fact that the ball's been fired horizontally. If you also check the ball's horizontal motion, you'll find that the distance between the images horizontally stays pretty much the same because the horizontal velocity is constant. And you'd expect that because there are no forces that way. Now you could be given more difficult questions where, say, cars driven off a cliff and they've actually measured the cliff to be a certain height. Let's say this cliff has been 10 metres high and the car actually lands 22 metres away. Now you could be asked to do a problem-solving question here, like how fast was the car travelling when it left the road. So that's not the typical one like I've just been doing with you. This is a bit more difficult. But if I would still approach it the same way, that you need to do a horizontal and vertical components here and then just sort of see if you can piece it together. So normally the time is one of the key things to find here. So when you look at it, there's not much there, but we can always go A equals 0 for the horizontal. We can always go A equals minus 9.8 for the vertical. The other information we've got is that the starting velocity vertically is 0 because the car's not flying, it's not going up and down, I presume. Horizontally, we do not know what that velocity is. That's what we're trying to find out. So how do you get to that? The other information we've got this time, though, is we've actually been told how far it goes when it lands. So we've got that part there for a change. Okay? And we know that it's going to go down minus 10 metres. So there's the information we've got. Which column can we start working in again? Well, we could try and work here until we get the time. S equals VOT plus a half AT squared. Is that something that we can do here? We've got 22 metres. It's going to land 22 metres away. The acceleration here is 0. We've got a starting velocity we don't know, but we do not know the time, so we're stuck. All right, so we can't do that at the moment. So what we need to do is find the time somewhere. So the time is normally based on how high was the object in terms of that. So can we find the time over here is the question then. So if we look at that, we are going to do something along the lines of what we've done before, S equals VOT plus a half AT squared. But this time we're going to have to find the time again. So we've got minus 10 metres. This has got a starting velocity of 0, so we can cross this out again. Now the half of minus 9.8 again is minus 4.9 t squared, and this again should look familiar to what you've just been doing before. All right. So again, you would do minus 10 divided by minus 4.9 instead of times it by minus 4.9. That's the opposite. And we're going to square root that to solve that. So it's the square root of 10 over 4.9. So you're going to get about 1.43 seconds there. All right. So now, because it's a scalar quantity, we can actually put the time up here and finish this off. VO times by 1.43 seconds. So to solve this here, we're going to try and rearrange and get rid of the times by 1.43. So we're going to do 22 divided by 1.43, and that's going to tell us our VO. And we're going to get about 15.4 metres per second for the car.